this diagram, let me just run through it in 5 minutes, the important points, and please tell me if you think everybody can get it, yeah? So this is, if you like, a mixture of tangible geometry, because I'm showing 3 lampposts, let's say, or 4 lampposts, going on a line, right? They're all the same height, and I'm looking at a cross-sectional view of it, and I would see them all the same height. If I step back far enough away, I know these lampposts are all the same height. That's exactly what I would see, right? Yeah. The tangible, these objects. And I've put now our circle of measure in here, so our arc, so that we can see what actually happens. Now, as the top of the lamppost, or I move to the second lamppost, then the position of that second lamppost is going to fall down on the arc from N to O. So it's going to drop in its visible position. And when I say visible position, I do mean that. I don't mean its tangible position. Its tangible position isn't moving. It's fucking nailed into the ground, right? It's not going anywhere. Its visible position is dropping in my field of view the further away the top of that lamppost goes, so that I go from N to O, from O to P, and from P to Q. And basically, if I continued, then that's going to drop all the way down to this blue line, i.e. my horizon, yeah? And the ground is going to do the same thing. The bottom of the lamppost is going to start rising to the horizon. The ground rises to the horizon and the sky falls, right? We're all agreed on that. And the very fact that I am now closer to the bottom of the lamppost than I am to the top of the lamppost, if I was exactly in the middle here, if I was at 3 units in the middle between 0 and 6, then both of these things would converge at the same time. And the thing would shrink and smaller. With the same at the top and the same at the bottom, it would shrink and get there. But that only happens if I am in the middle, equidistant between the top and the bottom. If I am not equidistant from the top and the bottom, then other phenomena occur, which is what I've tried to describe in that document. It's not the same. This simplistic way of looking at perspective, that things get smaller in the distance, and it does so proportionally above and below, is only true if you're equidistant from the top and the bottom.
That's actually mentioned by Rowbottom in his original book.
It is, yeah. He explains it as well with straight lines. He doesn't use the arc, which, I think...
No, he doesn't use the arc, but he explains that if they're equidistant, they'll disappear at the same time. They'll converge at the eye line at the same time.
So if I'm just looking at this red line, if I imagine I could see a red line, a roof, and I have a floor, then the roof and the floor are going to converge to my eye line, or to my horizon, if you like, if we want to call it that too.
Which is why boats disappear bottom up, because they convert if the sails and everything are higher above your eye line than the hull is, then that bottom section is going to disappear, reach the eye line before the sails.
Yeah, well, actually, it won't reach the eye line. They're going to both reach the eye line at the same time. But what will happen is you will reach the limits of vision, and you will reach the limits of angular diffraction at the bottom quicker.
Yeah. Well, no, they still converge at different times too, don't they? That's what you were just saying.
Yeah, but exactly where they converge at infinity, right? Mathematically spoken, they both converge at infinity. But the one at the bottom will reach the limits of vision and the limits of angular diffraction quicker.
I gotcha.
I think it's an important distinction to make, because I don't believe in infinity anyway. I'd rather see indefinite. So you have a finite length and you have an indefinite length. I hate that word infinity, because it's just a mathematical trickery.
Is that sort of why you can't draw this diagram to its full extent?
Yes.
Because that convergent points is just too far in the distance, too far to the right.
Yep. Yeah, you would have to be so far away to take it all in one view that you wouldn't be able to distinguish it anymore. if you like. So again, we reach our limits. But just to go through the argumentation, so when you look at the horizontal spacing between two things, then if I go from H to A, then the horizontal spacing is moving from U to T. And when I go from here, from A to C, it's going from T to S. And when I go from C to F, it's then going from S to R. Those are the 4 points that I have there. And this angle here between S and R, if you can imagine that this angle here, the difference between these 2 points is going to be, when I go further away, so small as to be insensible. And that's when the limits of vision are reached. And when that happens, and it's probably due to the fact that we only have a certain amount of rods and cones on the back of our retina, that we can make that differentiation. But basically that angle is so small that we cannot longer differentiate between these 2 points, from our eye limitation. And that's when this whole horizontal space disappears from view. And anything sitting in that horizontal space also disappears from view, because you can't tell one point from another. And if you go even further to the right, then the same principle kicks in with angular diffraction, the Rayleigh criteria, which basically says that 2 light points can't be distinguished from each other. So you have the vision limits of the eye, and at some point you have the visual limits of nature. And when that happens, those points are no longer distinguishable. Anything in this interval is then lost to sight because it's no longer distinguishable. You cannot see it anymore. And you can see from the top half that the angle's still a lot bigger, right? So this angle has not reached that limit the same way the bottom part has reached the limit. The bottom is always going to reach that limit sooner because you're closer to the ground, or closer to the bottom of the object in this case.